Hello, it is Ryan Winterhalter, and I'm here to do my Skill 15 video. So, for Skill 15, the objective is to learn to work with geometric sequences and series. So my problem says a bug leaves the point 0, 10 on Monday and crawls 480 units out along the positive x-axis. Then on Tuesday, it turns around and crawls 120 units back toward the y-axis along the line y equals 10. Then on Wednesday, it turns around again and crawls 30 units away from the y-axis along the line y equals 10 and continues along this pattern for the days that follow. Determine how far the bug has crawled from Monday to the end of the day on Friday. Then determine the coordinates of the bug's ultimate destination if it continues crawling this way forever. Be sure to include appropriate terminology and notation in your experiment. Okay, so basically, we start here on Monday, and if this is the y-axis, all of this is happening on the line y equals 10, but the bug on Monday travels 480 units this way. Then, on Tuesday, it travels 120 units this way. Then, on Wednesday, it travels 30 units this way. On Thursday, it travels 7.5 units this way. And then on Friday, it travels 15/8 units this way. So, basically, here is what it looks like on an actual graph. It starts here at the point 0, 10, travels all the way out here on Monday, then on Tuesday, then Wednesday, then Thursday, then Friday. And the distance it travels gets smaller every single time. And when we look at these numbers up here, we're able to determine that when we divide by 4, from 480 we get 120, then we divide 120 by 4 to get 30, then we divide 30 by 4 to get 15 halves, then we divide 15 halves by 4 to get 15 eighths. So we know our factor here is going to be 1/4. And now the equation for a geometric sequence is your starting term times your rate of growth or decay, or whatever your rate may be. In this case, ours is 1/4, to the power of n minus 1, where n is the term value in the sequence, and that gives you whatever value you actually have for that term. So basically, you take your starting value and multiply it by this term over and over and over and over again to get whatever value for a certain term in a sequence. So, plugging in our numbers, we start at 480 and our factor is 1/4. So, an equals 480 times 1/4 to the power of n minus 1. And basically, what this says is that we take our starting value of 480, and for every day or term, which is n, for every day that we go on, we multiply by another 1/4 to keep decreasing this 480 to 120, then 30, then 15 halves, then 15 eighths, and so on. And remember, n is the term in the sequence. So for term 1, we plug in 1 for n and solve for a of n, which is 480. And that works for every single term in the sequence. Now, the problem is asking us to determine the total distance that the bug has traveled from Monday to the end of the day on Friday. So for the first 1, 2, 3, 4, 5 terms. So we can write this in sigma notation. So for total distance, what we have is we will start with our first term, which is y n equals 1, and we will go to term 5. And then we have our geometric sequence here, which this tells us that, as this work shows, we are taking 1, we're starting at 1 and going to 5. So we plug in 1, 2, 3, 4, and 5 in for n, solve them in our geometric sequence, and then add all of them up. When we do that, we get 639.375. So when we use sigma notation, we can see that all of this can be simplified into this simple notation, where we have our starting term, where we have what term we go to, and we have our actual geometric sequence itself, which will give us, as we see here, the different values in the sequence. And what sigma tells us to do is to add all of these terms up in the sequence, making a series. So now that finds us the total distance it has traveled in the first 5 days, but what about the total distance from the y-axis? So when we look down here, because it travels back and forth, we have to make our rate -1/4. So that way, on the first day it travels 480, but on the second day it travels -120 because it's going back towards the y-axis. Then 30, then -15/2, then 15/8. The reason we do this is because on the days that we have an even exponent, then this -1/4 is positive, because as you can see from our original problem, on the even days like the first day and the third day, things in here that would give us an even exponent, the bug is traveling away from the y-axis. But on those days where we would get an odd exponent like Tuesday and Thursday, the bug is traveling back towards the y-axis. So we have to change our 1/4 to -1/4 to account for the fact that the bug is traveling back and forth away from the y-axis, then back towards it at a smaller distance, then away from it again, and so on and so on. So what we do here again with our sigma notation is we have n equals 1 because that is where we are starting. Then we have the term that we are going to, which is 5, because we are only finding Monday, Tuesday, Wednesday, Thursday, and Friday. Then we have our geometric sequence here. That is our starting value times our rate, which we changed to account for its change in direction, to the power of the term minus 1. And so when we find all of these values, we get 384.375. That accounts for the bug's change in direction, it going 480 units away from the y-axis on the line y equals 10, then back towards the y-axis on the same line 120 units, then away 30, then back towards -15/2, then away again 15/8 of units. So what this sigma notation tells us is that we take all of these values for our n values, 1 through 5, and then we add all of them up together. And that gives us our 384.375. Okay, so now for the second part of the problem here, where it's saying if it continuously goes along with this pattern, how far will it have traveled if it goes on forever? Okay, well, a little background here so we can find the formula that we need to use. So let's say we have a certain series. This S will represent the sum. We take our initial value, A1, let's supposed to say A1, plus A times the rate, plus A times the rate again, as our formula over here shows us. We keep multiplying by the rate every term value we go up, and that keeps going on and on and on and on and on until we reach A times Rn minus 1, right? Because that's right up there. That will end up, we can plug in any value for n there depending on how far we need to go in our sigma notation. So then, now let's say we multiply the entire thing here by r. So we get S times r equals AR plus AR squared plus AR cubed, because we're multiplying each of these values by 1r, which is why the exponent for each one is increasing by 1. Now, over here, we will have this same thing, but this will actually become AR to the power of n. Because if we multiply by another r, that gets rid of the n minus 1, because n minus 1 is the term before, r to the power of n minus 1 is the term that would represent the term before a times r to the power of n, right? So when we multiply by r, we're going to the next term, which is what we do in our formula over here, which is why this gives us a times r to the power of n. And we don't have to subtract that one because we don't have to go to the term before. Now, when we subtract these two formulas, we get s minus sr, so the sum minus the sum of the second one times r equals the starting value minus the starting value times the starting value times r to the power of n. Everything here in the middle cancels out because this is the only thing left, these two cancel, there will be an AR cubed here, so those will cancel, then everything in between will cancel out, including this AR to the power of n minus 1, because that's here and here. The only thing that this one has that this one doesn't is that it goes one term further, which is why we don't have the n minus 1, but rather just the n here in the end. So that will go down here because that will not cancel out. Then we can factor out an s from this side and the starting value, or a, from this side. That gives us s times 1 minus r equals the starting value times 1 minus r to the power of n. So then we divide by 1 over r, giving us the sum of the series forever, as this shows us here, because this goes on forever. S equals the starting value times 1 minus r to the power of n over 1 minus r. But because our r value is less than 1, r to the power of n will get really close to 0. So in theory, if it goes on infinitely, it will equal 0, correct? So s equals the starting value times 1 over 1 minus r, right? Because if you think about it, if we have a decimal and we keep multiplying by that decimal, what happens to the number? It gets really small, right? Well, so then, excuse me for a sorry about that. Okay, so if we keep multiplying by that decimal, it will get really small, because if I take 1/4 and then I multiply that by another 1/4, then we get 1/16, which is smaller than 1/4. And then if we do that again, then we get an even smaller decimal. And so we keep going along that pattern until we reach 0. And that's why we can take out that r to the power of n, because if our r value is less than 1, which it is, it's 1/4, then it'll get infinitely close to 0, which means that we can set it equal to 0 for the purposes of our formula here. So then what we're going to do, because we need to find we need to find if the bug continues along this path forever, where it will end up. We can do this for both the total distance it travels and the total distance it is from the y-axis. And so we just have to use our two different sigma notations here. Our first one, as we had up here, where our rate was 1/4, we just have to go to our formula and plug in our starting value times 1 over 1 minus the rate, which is 1/4. When we simplify that, we get 640. So if the bug travels along this path here, as explained in the formula, or in the problem, forever and ever, eventually it will have traveled a grand total of 640 units. Now, if we want to find, after it travels on and on forever, we want to find the distance it sits from the y-axis, we just have to use our other sigma notation, which our starting value is 480 and our rate is -1/4. So right here we have s equals 480, our starting term, times 1 over 1 minus our rate, which is -1/4. So when we simplify that, we get 384. So in the end, if this bug travels along this path forever, it will end with an with a value of 384 units away from the y-axis. And because the problem was asking us for the coordinates of its final position, and the bug only goes left and right, it never goes up and down, and it says it's on the line y equals 10, we know that the final coordinates will be 384, 10, because 10 will not change. It stays on the line y equals 10 the whole time, so it'll start on the line y equals 10, and if it goes on and on forever, it will end on the line y equals 10, which it does here. And we also found that the distance it will be from the y-axis after all of this will be 384 units, because it starts on the y-axis, and after we use our sigma notation and our knowledge here to cancel out Rn after finding the formula and plugging in our numbers, we were able to find that the total distance away is 384 units, which is why the final value for the coordinates of where the bug will stay, if it goes on and on this same pattern forever and ever, will be 384, 10.